Okay, sure.
Okay, thank you for coming, and let's start today's talk. Today, Dr. Tumpa Mahato from India Institute of Technology, LOPA, will give a talk about the arc shift move and region arc shift move for twisted knots. Let's welcome Tumpa. Please start.
Sure. Thank you so much, Kim. So, as he said, we are going to talk about arc shift move and region arc shift move for twisted knots. This is a joint work with Dr. Madhiti Pravakar. Let me know anytime if my audio is not right. Okay. Okay, I'll just start. So we are already familiar with classical knots and virtual knots, where you can consider classical knots as knots in a thickened sphere. Virtual knots are generalization of that, where instead of taking thickened sphere, we are taking thickened orientable surfaces.
Excuse me, you haven't shared your screen.
Oh, I have actually.
Oh no, I can see the screen. Oh yeah, I can see. I'm looking the slide. What are twisted knots?
Yeah.
Is it right? Yeah.
Yeah, Tumpa, I'm
Sorry,
very glad
I can see. Sorry.
I'm
Thank you. Please
I'm
go
glad
on.
to see. Yes, I'm glad to see you, Tumpa. And yes, so let's start our today's meeting. Our speaker
Oh,
is Tumpa Mahato, and she will tell us about
sorry.
arc shift move and region arc shift move for twisted knots. Let's welcome.
Okay, so I'll start again then. Okay, thank you. Okay, so I was just talking about we are already familiar with classical knots and virtual knots, where classical knots are knots in a thickened sphere, and virtual knots are knots in a thickened surfaces with the genus not zero. So, like orientable surfaces, torus or n genus surfaces, where we have in the diagram we have marked the virtual crossings with a circle. That's the difference from classical diagram and virtual diagram. Now, twisted knots are generalization of virtual knot theory, where the surfaces now may be not necessarily orientable, they can be non-orientable too. So in the left side figure, that is a thickened Klein bottle, that blue and red square, that the Klein bottle. And in the diagram, this is a one foil twisted knot. And there are two bars. So like in virtual crossings, you have a extra marking with a circle. Here we have another extra thing, which are bars. Now what the bar do? This bar will denote that the path near the bar around the knot will uh, will have a reverse orientation. Will change the orientation near the bar in the when the link is embedded on your non-orientable surface. Like here, there are two half twists in this Klein bottle. Uh, you have to identify this red arrow to the red arrow with a half twist. So that is one bar is for that. Another bar is for when you are identifying the blue arrows. So this denote the bars are the new thing in the twisted diagrams. On the right side, this is another concept, abstract diagram, where you can see, because this is a ribbon-like structure, you can see the ribbon is twisting near the bar. So the orientation is reversed. So this gives us the idea that the knot is in a on a non-orientable surface. Now, so today we will only talk about the diagrammatic side of twisted knots. So when we talk about diagrams, so we have new moves added to we already had the generalized Dreidiemaster moves for virtual knots. So R1, R2, R3, V1, V2, V3, V4, we already know. So we have three extra twisted moves which are where virtual crossings and classical crossings are involved with the bar. The first one you can see, the bar can cross the virtual crossing. Second one is two bars, consecutive bars which cancel each other. The third one is these virtual crossings can be replaced with bars like as shown in this figure in the T3 move. Now, okay, so yes.
Sorry. Can you explain again what was the geometric interpretation of the bars?
Yeah, so like in the virtual case, the surface was like torus. So yeah, now the surface can be a Klein bottle or real projective plane, where the orientation can be reversed in near the knot. So here you can see these two black arrows on the left figure in the cube. That is the actually the knot. So you follow the knot like this. I will say vertical. Let's say vertical. So follow the vertical black arrow. You hit the blue arrow. Now you have to go to the other blue arrow, but you have with a half twist. You can't just identify those two blue arrows because the arrow because of the orientation. You need a half twist. That change of orientation is shown in the diagram as a bar. So the knot is the knot is like a one-dimensional thing. You can't see the change of the orientation, but in the abstract diagram, you see the ribbon is changing with a half twist near the bar.
Okay. And this blue-red diagram which you have drawn, is that Klein bottle?
Yeah, sure. Yeah, that is Klein bottle.
Okay. I guess I'm not familiar with this one. I'm
Yeah,
familiar with.
this is a different one. I also checked.
Okay. Thank you.
Yeah. Okay. So should I go to the next one?
Yeah. Thank you.
Yeah, sure. So like so the now in the Gauss diagram also you have to put the bar wherever between the crossing you have a bar, you have to put it on the Gauss diagram also. In the Gauss code 2 you have to put a B where there is a bar between two crossings. So that how you are representing the bars in a Gauss diagram or a Gauss code for twisted knots. Now so now the forbidden moves. So we already have F1, F2, F3, F4 for classical and virtual knots, those 4 forbidden moves. Now we have an extra forbidden move, which is called T4. This is like a first tridimensional move with a bar. So you are not allowed to open this loop if there's a bar inside it. Okay, and the right side is just the Gauss diagram representation of the forbidden move. So it has been proved that if you apply T4 F1, so because of the twisted, I have written or F2 or F4 because under all the twisted moves, F1 F2 are equivalent and F3 F4 are equivalent. So you can take T4 F1 F3. If you allow these three moves, any twisted knot diagram becomes a trivial diagram.
Excuse me.
Yeah.
Excuse me. And what about parity theory for twisted knots?
Can you
Do you
repeat the
have a
question?
classification? What about the parity theory for twisted knots? Do you have a classification of parities?
What do you mean by parity? Which parity are you talking about?
Well, I'm talking about standard parity, where we have even and odd crossings which satisfy parity axioms. So that is so useful in virtual knot theory. Standard parity.
Yeah, I am not familiar with the parity axioms, but I've seen in the when defining a polynomial invariant or any invariant, the parity thing has been used for the bar also. So if you smooth a crossing, you have two components, and how many bars
For
are there?
example, this is one of yeah, okay, so good. Good. You may update and you may improve many invariants by using parity.
Yeah. So I will later show invariant where this has been used. The number of bars is even or odd in in any component.
Okay.
Okay. So okay. So one important thing is here that there are two trivial diagrams for twisted knots. I haven't put a figure. So one is the usual trivial diagram with no crossings, no bar, and another one is no crossings with one bar. That is also considered as a trivial diagram. So we have two trivial diagrams in twisted case. Okay. Okay, now there are some invariants which are generalized from virtual to twisted case. One of which is odd right. We already know what is odd right. Sum of the signs of all odd crossings, right? So that is also invariant for the twisted knot also. The odd right for any twisted knot diagram. This we will use in the next slide. So there is an. I forgot the lemma.
Yes,
Okay.
so actually, odd right is an invariant if you take all odd crossings for any parity. So if you have other parities, you can use odd right for any parity.
Yeah.
Yeah, okay.
Okay, so now I want to talk about unknotting operations. So this is a one foil twisted knot diagram, and you can see even you change the crossing to over to under, it it is the same. You can't unknot this knot because of this that forbidden move T4 that looks like R1 with a bar. So you can't open this loop. So crossing change is not an unknotting operation for twisted knots. So this cannot be generalized for twisted knots, this unknotting operation, but few can be. So one of which can be generalized is arc shift move. What is arc shift move? So on the left figure, you have a twisted knot diagram. An arc is you take points on the edges, not the crossings, like C and D. And this arc should have only two crossings. The crossing may be virtual also. Virtual is allowed. So only two crossings. Like CD is this blue one is a arc. CD is an arc. AB is also an arc. The difference is AB has a bar and CD has not. So bar is also allowed. So arc can be anything. Classical and virtual crossings are allowed.
And can you draw? So excuse me. On the left, you have a picture.
Yes.
And do you have? So what is the image of this picture? So so on the right you have a move on Gauss diagrams, and on the left you don't have a
No. On the
a move.
right, this is also a not part of the local part of the diagram.
Can you draw it in terms of just usual diagrams, not Gauss ones?
This move. Actually, I will
Yeah,
show what it looks like. I will tell what it looks like in Gauss diagram. That is actually much easier to see.
yeah, okay.
Okay, so the arc, first I defined the arc. What is an arc? So in the diagram, so figure B on the left side, any knot diagram, you have two consecutive crossings. This circle can be any crossings, classical or virtual, and there is a orientation. So you are going from A to B. Now the move is, instead of following this direction from A to B, you will maneuver and first go to B, then go to A, then follow the knot orientation as you are following. So what is this doing? It is changing the order of these two crossings which I have put white circles. So whatever these crossings are, the order has been changed and also the signs also are changed. So in the Gauss diagram, what we will see, two consecutive crossings over under, it does not matter. It will change the order along with the signs. So this is different from the forbidden move. In the forbidden move, the Gauss diagram has two consecutive over tail of the arrows are changed, right? The order is changed only. In this case, the order is changed, the signs are also changed, and it need not be over. It can be over under. There can be a bar in the middle also. So I will show that. Okay. So there are two types of arc shift move. So if there is a bar in the middle of these two crossings, I will call it type 2. If there is no bar, so type 1. And this is one of the examples. This can be under, over, or a virtual. So for each case, you have multiple number of type 1 arc shift move and type 2 arc shift move. The main thing is the order of the crossings are changed and the signs are changed. Okay? Okay, I'll go ahead. Okay, so it has been proved that if you apply arc shift move in a twisted knot diagram, you can transform it to a trivial twisted knot diagram. This proof has been done like this. So if you can prove that the forbidden moves are realized by arc shift move, that how the proof goes. And since now arc shift move is an unknotting operation, you can define the arc shift number. So minimum number of arc shift move needed to transform a diagram to a trivial diagram over all the diagrams of any knot, like how we define any numerical invariant. So this number is this all this work is done by Komal Negi and Madhiti Pravakar. So I put the reference below. Now there's a relation between this arc shift number and the odd right I mentioned before. So odd right gives you a lower bound for this arc shift move, which actually really helpful to compute the arc shift number. Okay. Next, okay, so this is one invariant I want to mention. This is work by Naoko Kamada. So I'll just explain what is happening here. So start with a twisted link diagram. Take any self-crossing. You smooth it. You get two components, like over component and under component. Now for each component, we will compute two values. What are the values? Uh, this is just the indices of the crossing, how we compute. So for any component, whenever you encounter a overcrossing, take the negative of the sign. If you encounter a undercrossing, the sign remains same, and take sum. That's how we calculate index of any crossing. You can take other method also to compute this index. You will have the same value. Now for every component you can do this, and now the first value is this row bar star C. This is 1 if the index is odd, if this is 0 if the index is even. So this row captures that data. And the another term is P star, which captures the bar data. In your component, if the number of bar is odd, then this P star is 1. And if the number of bars is even, this P star is 0. Star means star is either over component or to denote the component actually, O or U. So if you have this data, so the polynomial is like this. For every self-crossing, sine of C, S to the power rho bar OC in the over component, T to the power in the over component, the bar is even or odd. Similarly, for under component, the next term, if the index is odd or even, if the bar is odd or even. So this work is by Naoko Kamada and Saichi Kamada. And for this is for twisted link diagram. For twisted knot, actually the index is same, not same, but the parity is same. If it is even on one component, the other component also it is even. So in this case, so this remark is there. So rho bar OC will be rho bar UC. So we have to compute just one of those. And this is invariant, which I have used in my work. So that's why I have explained it. Okay. Okay, so we already it already has been proven arc shift number is an invariant. So what we did first, so we first wanted to find a knot for any if given any positive integer n, we have found a knot which will have a arc shift number n. And this is the knot. You can see this is constructed by adding the same block multiple times. This is one block and which has been added multiple times. So how it has been proved that first we have computed the odd right, which is 2n in this case, which gives us the lower bound n. And if we can show that there is a diagram with n number of move needed to transform it to a trivial diagram, then we can say the arc shift number is n. So you see that this block has been repeated, right? So what we show that this block, if you apply the arc shift move on this red arc, now this on this red arc you can see there is a classical crossing Ci and a virtual crossing. So if arc shift move is applied on this, then it becomes a parallel line. So each block takes one arc shift move to become a parallel line. So if I put it at every block, so every block actually eventually it reduces to this trivial standard trivial diagram. So there are n number of blocks, so n number of arc shift move you need to make it a trivial diagram. That's how we prove that this knot has arc shift number n. Now, one thing we notice that if I put it in one block, then you actually, so I have named it Kn. Okay, so this knot. If I do that transformation in one block, I will get kn minus 1, which will have arc shift number n minus 1. So actually we are getting an unknotting sequence of knots where at each stage of the sequence ki, the arc shift number is I. So now similar thing we did. Oh, also for every ki, we have found that polynomial invariant which depends on this n. So we know that each ki is different. So we have used the polynomial like this. Okay, so in the next one, we have given two unknotting sequences of twisted knots, where first one, so km, you apply one arc shift move, you will get km minus 1, and it reduces to k0, which is the standard trivial diagram. And the next sequence, k0 prime, is actually the other trivial diagram with 1 bar. So that's the different for k0 and k0 prime. Similar type of proof here. First, we have shown this local diagram with one classical crossing and one bar. I have first added one virtual crossing because I need two crossings to apply the move. So after that, I apply the arc shift move and I get this diagram, which is actually part of the, which is this vertical thing, which is repeated in the diagram. So now if I apply this first transformation in this red part, this eventually becomes one virtual diagram. So every vertical block in the Kn becomes one virtual diagram. So you can see every vertical becomes one virtual, and eventually by V1 move becomes a trivial diagram, and the second one becomes the other trivial diagram with one bar. The proof is similar, finding the odd right for the lower bound, which is same for both of cases n, and also we found we needed n number of moves. So for both these families, the arc shift number is n for nth place of the sequence. Also, we have used this Q polynomial to show that each of those, all the knots in those two sequences are different. Okay. Okay. So now region, arc shift move, and twisted knot diagrams. So we generalize there is already the concept of region, arc shift move for virtual case. What is a region? You can look at the figure. So you take the twisted knot diagram and consider it like a graph, where virtual is also an vertex of the graph. So this connected component, any connected component of that graph will be called a region. And you can see the edges can have bars. So like this R in this figure. Now, what is a region arc shift move? You take any region in your diagram and there are boundary arcs on the diagram. So for every arc you apply arc shift move. That is one region arc shift move. So like in this figure, one arc shift move on this R region has been applied, and it is actually the trivial twisted diagram with one bar. Okay. So we proved that this is our work. So we proved that this is an unknotting operation for twisted knot by showing that first figure shows that FT move, the second forbidden move, can be realized by one region arc shift move. So in the forbidden move, we have a triangular region with the two classical, one virtual. So on the boundary arcs we have applied. So I have denoted A, B, C, D, E, F. These are the arcs where the move has been applied, and it is easy to see in the Gauss diagram. So you can see this is the first Gauss diagram. Then the arrow ends change their order along with the sign. So epsilon 1 becomes minus epsilon 1 and epsilon 2 becomes minus epsilon 2. And now the next arcs have CD and EF has one virtual crossing, which you cannot see in the Gauss diagram, but you just see the sign changing. So the left one and the right arrow, both of them change sign because action move is applied with a virtual crossing. So finally, you get the Gauss diagram, which you get after applying a F2 move. Similarly, for F4 move, that bar does not disturb this process. And we can prove that F2 and F4 can be realized by one RAS move. there is another forbidden move, the T4 one, which in the diagram only, not diagram only, we can prove. So you have to add one virtual crossing because we need two crossing to apply the move. Then we have taken this dotted region where we apply on every boundary arc the arc shift move. It eventually becomes this. What is the T4 move actually? So this proves that region arc shift move is actually a unknotting operation for twisted knot. The next thing is to define the region arc shift number. So minimum number of region arc shift move needed to transform a diagram to a trivial twisted diagram and over the all diagram. And this becomes an invariant because we are taking the minimum. And this is an example where after applying the region action move on this dotted region, it becomes trivial. So the region action move is 1. Oh, so this is also non-trivial. You can check with this that Q polynomial. So, okay. Oh, since the forbidden moves are realized by the region action move, so you can directly say that is the proof of this theorem that the region action number will be less or equal to forbidden number for twisted knot. Forbidden number means minimum number of forbidden moves needed to transform a twisted knot to a trivial diagram that can be F1, F2, F3, F4 or any set of forbidden moves. This example is one example where the inequality holds strictly because the forbidden number is 2 and the region action number is 1 here. You need two F2 moves here to make it a trivial diagram. Next, we tried to do the same thing for this also to find a knot which has a region action number exactly in, but because we don't have a lower bound, we can't say exactly in, but we found a diagram where applying n number of region action move, you get a trivial diagram. So here also this vertical local part is repeated n times and the dotted region is where you will put the region action move, and I will show what happens when you put it. Okay, so this is the vertical part where I've written horizontally. In the dotted region, there are two boundary arcs where the region action move has been applied and it becomes an one virtual crossing. So every vertical part becomes one virtual crossing and which gives you the trivial diagram. This only gives you the upper bound is n for the region arc number. So the next thing we want to do is find a lower bound for region arc number using some invariant actually. So next what we did, because we couldn't find the lower bound for RAS, we took the forbidden number of twisted knot diagram and we tried to find a lower bound for it. What we did for that was we will find the changes in the terms of this polynomial after applying a single forbidden move from this set for every case F1, F3 and T4. So let's, for example, the first figure is for F1 move where you can see the over arrowhead. Okay, arrowhead is changing the order. So for C1 bar, now the index, if before the move is index is even, after the move it will odd. So it will change to odd to even and even to odd for both the crossings. Also the signs are same because it's an F1 move. Okay. So also there is no bar involved between C1 bar and C2 bar. So bar number is not changing. So if you remember in QST, there was a term P0 which captures the data if the bar number is even or odd. So that is not changing. So that's what we did. We collected these changes, what is happening with the number of bars and the indices for F1 case. For F2, F3 case, you see there is a bar between C1 bar and C2 bar. So when they change the order, so number of bar is also changing from even to odd or odd to even with the indices also. And the for T4 case, the crossing is not there on the right side. So we capture this change and the propositions. So this proposition gives you the change in the polynomial for F1 move, which these are all the cases given 1, 2, 3. So these are all three type of polynomial we get. after applying one forbidden move F1. Similarly, we did for also there is two cases depending on the total number of bar of the diagram is even or odd. Depending on that, the polynomial looks like this. Same thing we did for F3 or F4, it looks same. So there is also two cases. If the number of bar is even, total bar, and the total number of bar is odd. So there are two cases where three values are given. This M1, M2, M3, the coefficients. And for T4 also we found the difference, which looks a little bit nicer. Okay, so depending on number of bar is even or odd. So now using those proposition, we proved that for any twisted knot diagram, the forbidden number will be greater or equal to odd right divided by r if the bar number is even, total bar number is even, and it will be divided by odd right divided by 2 if the total number of bar is odd. How is it? I will give a brief explanation of the proof. Let's say the forbidden number is n, and starting from k, let's say k is kn, you have this sequence of knots k, kn minus 1 to k0. So each ki to ki minus 1 is one forbidden move. Applying one forbidden move, we are getting ki to ki minus 1. And the last k0 is your trivial twisted diagram. Okay. Next, what we did was, see, case 1 is number of bar is even. Okay. So if you remember the polynomial structure, there were two terms in the polynomial. Maybe I should just go there. Wait, this is 38, right? Yeah, here. Okay, so look at the polynomial. So there are this P0C and PUC. There are two components where the bars are divided, right? If the total number of bar is even, so the division can be even and even, right? So either 0, 0 or odd and odd, 1, 1. Okay, so it cannot be 1, 0. So if t is there in the polynomial, so there will be 2 in both the terms, the t will be present in when the total number of bar is even. Now when the total number bar is odd, the division is only 1 and 0 or 0 and 1. So t cannot present in the both of the factors, right? So there is, you can write the general term for QST where the total number of bar is even and total number of bar is odd. So that's what I have written there. Oh, sorry. Yeah, so when the case 1 is total number bar is even, all the terms has either t is not there in both the terms, so s minus 1 square is there because of that, or t remain in both the factors. That's why st minus 1 or t minus 1. And here an plus 1 and bn, these first two coefficient, sum of these two coefficient actually the odd right, because the s terms is there means the indices are odd. So using this, so the difference between the polynomial for k0 and kn, now you can write it for, you can add minus qk1 plus qk1 like this. And each term on the right side is actually one move, one change in the polynomial, which we already have computed in the propositions and which we applied here. And by substituting a specific value of s and t, we find this relation. On the left side, a1 plus a2, which is actually the odd right, and n is the forbidden number. So that's how we get this lower bound. And for when the total number of bar is odd, as I said, t cannot be present on both the factors in the polynomial. So in general, the polynomial looks like this: st minus 1, s minus 1, where a4 will be the odd right actually, because other terms where s is 0, those are the even indices crossings. So similar here, we get the lower bound is odd right divided by 2. So this thing we couldn't do for the region arc shift number. The problem is the change in the indices actually depend on the number of boundary arcs of the region. So it varies with the number of the boundary arcs. So we could not, the right side is of this, like this first, not this one, the first line here, just one arc shift move change. We are not, that is not a fixed change in the indices value because it depends on the number of boundary arcs. And you don't know at which region the move is applied. Okay, so that is the problem with the region action move. So that is what we want to do next, to find a lower bound with some help of some other invariant, maybe not this one. So that was all in this talk. These are the references. The first one is the first paper in twisted link theory by Bourgeois, who defined this new generalization of virtual knot theory. And there you can have other invariants also, like knot group, Jones polynomial. Everything is explained in that paper. Other is about this unknotting operation and the this Nauka the Saichi the paper invariants of this is the QST polynomial invariant paper, and these are all. Thank you.
Okay, thank
Okay.
you. Okay.
Yeah, thank you very much. Are there any questions or comments? Actually, I have one question.
Yes.
You introduced two unnothing numbers, the region shift, arc shifts, and usual arc shifts.
Yes.
Are there relationship between the number of another number of the unnothing number for with arc shifts and region arc shifts?
Between these two.
Yeah.
Oh, so the same problem what I said. The problem is the region arc should move. One region arc should move. I don't. It depends on the number of boundary arcs of the region. So we can't find a. We can't prove that because of that problem. If anyone has any suggestion on that, how to capture that data or how to overcome that problem with the number of boundaries of the region.
I see. I see. Thank you.
Because every every crossing on the boundary arc, it appears twice in the boundary as a over and under, and the indices actually change. It does not change the sign. So one arc shape move change the sign, but you changing the sign twice because one crossing belongs to two boundary arcs. The sign is same. The indices are also not changing. So anything related to indices is not working for this type of relation. So I have to find some other invariant or other property to find a relation.
See. Thank you.
Okay.
Oh, I have one more small question here. Region arc shift is motivated from the region change, as I remember, the by
Reg-
Ayaka Schmitz.
oh, that was
Crossing.
region crossing change.
Oh, yeah.
So actually, region action move is already done by. So the third one is actually, I think maybe it's second or third one by Gil Pravakar. They have, this
I
is for
see.
virtual nodes. Yeah.
I see. Okay. Thank you.
Okay. Thank you.
Are there any more questions or comments? If not the case, let's next speaker again. Thank you very much for this talk. Thank you.
Thank you so much.